This is going to go a bit off topic, but would you be able to explain to us who don't know what string theory is, like a brief explanation of what is string theory?
Sure. It's a proposed answer to a question. So let me tell you what the question is.
Hello everyone, welcome to Cambridge from the Inside. Today we're here with a new guest. Would you like to introduce yourself?
Yeah, hi, I'm Ron Reid-Edwards. I'm a fellow and director of studies in mathematics, and I'm also a member of the High Energy Theory group in the Department of Applied Maths and Theoretical Physics.
Nice. So today we're going to be talking about studying maths at Cambridge. So to start off, I mean, I've heard when it comes to the maths course that Cambridge is one of the most prestigious universities in the world to study maths. Is that the case? And if so, how come?
I'm obviously biased, but I think it probably is the case.
Mm-hmm.
Whether it's the best, I think, depends on taste, but it's certainly one of the best. And I think that's because of a number of reasons. Firstly, historically, a lot of big events in the history of mathematics have happened in Cambridge. So if you look at my area, which is theoretical physics, we had Isaac Newton, we've had Stephen Hawking, we've had Dirac. In fact, Stephen Hawking did his kind of groundbreaking work on Big Bang cosmology whilst a graduate student here in Trinity Hall. Mm-hmm. So, and then you look at other areas of mathematics, number theory, we've had Fields medalists here. So it's difficult to find another institution that has had such a big impact in a particular subject for such a long sustained period than Cambridge has had with mathematics. So in terms of its sort of global impact, it's been huge across the centuries.
Nice.
But as a place to study, we also have a very special teaching system, which I'm sure we will talk about at some point, which we're very proud of and we think is very effective and has produced over the years some of the best mathematicians in the world.
So as well as the success of previous mathematicians that have studied at Cambridge, how does the education, the course in Cambridge compare to other universities across the world?
So I think the biggest difference is the style of teaching, the way in which we teach. So in common with Oxford, we have what we call the supervision system. They call it the tutorial system. And the teaching is delivered in two modes. The first is sort of your standard classic lecture. Students from across the university, regardless of the college, will be in a lecture theatre and will go to a fairly traditional lecture. But the real jewel in the crown, I think, in Cambridge maths education, in fact, Cambridge education generally, it's not specific to maths, is the supervision system. And that's a system in which usually two students in maths will sit down for a couple of hours a week with an expert in their field and talk about problems in that field, talk about mathematics. And it gives those students an unrivaled access to expert knowledge. They can ask any question they like, and that expert will be there to develop their skills and their abilities and also their interest and enthusiasm for that particular subject. The other thing that's very particularly nice about Cambridge is its scale. It's very large. We've got a maths faculty with 2 mathematics departments. And so that's a lot of staff, a lot of experts in a very wide, broad range of fields. And so as you progress through the university, you're not kind of funneled into becoming an expert in that particular area of maths that the university has a strength in, because we have strengths pretty much across the board. And so where there are new areas of mathematics that are becoming more and more interesting, we have the sort of pulling power to hire staff, say, in machine learning to deliver courses in machine learning. So really you can develop an expertise in pretty much any area of mathematics, very broadly considered, you like. And that's not unique, but there aren't that many places that can do it on the scale that we do it.
Nice, wow, that's phenomenal. And I'm just quite curious about when you were talking about these two departments, what is it that makes them two departments and not like one large maths department, if you see what I mean?
So from the point of view of a student, you wouldn't know there were two departments at all. We function as a single unitary faculty, and the two departments work together to write exams, to sort of deliver the lectures, and so on. So as for a student, even up to being sort of fourth year Part 3 student, really doesn't see this distinction. And actually, as a researcher and a lecturer, most of the time it doesn't matter, but it comes into play with certain things, certain bureaucratic issues like applying for research funding. Then it can start to matter. It also means as well, when you've got such a large number of individuals, such a large research and teaching organisation, it can be very helpful to subdivide into smaller units just to make things run more smoothly. But as a student, you would never know.
Nice. Yeah, it's amazing how much support and how many people there are working in the maths department for the undergraduates and postgraduates. So going back to the teaching, how many lectures and supervisions would a typical maths student have, and like, does it change throughout the years of their course?
Let me start with the first year.
Yeah.
So in the first year, you'll have, let me think, you'll have 2 lectures a day, every day except Sunday.
Okay.
So that, you didn't miss a trick there. That means at the moment there are lectures on Saturdays.
Okay.
And then you'll, in addition, have 2 hours of supervisions a week. So you'll be lectured in 4 topics each term, and you'll have a supervision in each topic every other week. Okay, so that'll be, say, if I'm teaching you for relativity this week, I won't see you again till next week. So you'll have an hour with me, an hour with one of my colleagues later on in the week on a different topic, and then we will see you again in a fortnight's time. Okay, so we rotate through. The reason I can be so confident about the hourly contact rate in the first year is that everything is compulsory in the first year. In the second and third years, you start to be able to make choices and specialise in things that you're more or less interested in. And there's an extent to which you can also tailor your workload above a certain minimum to sort of stretch yourself a bit more if you want. But generally speaking, that number of supervisions, about 2 a week, it's about right. Sometimes people push it up to 3 or 5 supervisions every 2 weeks, but it's about that amount. So it doesn't sound like very much, just that 1 hour's contact time in a particular subject every fortnight. But in the meantime, you'll find yourself very busy keeping up with the lectures, working through the problem sheets, which would be the basis of what we discuss in the supervisions.
Nice. So am I right in thinking, so in the first year, every 2 weeks, I would meet across the 2 weeks 4 different academics in maths for my supervisions?
That's right. Yes.
And they all have like different specialties.
Exactly. Yeah. So and it becomes more and more specialised as you go through. So it would be quite usual for you to have all of your first year supervisions in a particular term given by fellows in the college. But then as we get to the second and certainly the third year, we have to start to work a little bit more coherently as a university. So if you're wanting to take a course in general relativity, I can happily supervise you. If you want to take a course in statistics, you definitely wouldn't want me supervising you. And if you wanted to take a course in fluid dynamics at the third year level, there probably isn't anyone in, for example, Trinity Hall who is expert enough to teach you fluid dynamics at that level. So you'd be supervised by a supervisor in another college. And similarly, other students in other colleges will come to Trinity Hall to be supervised by our fellows. So as we work our way through the years, we start to act a little bit more like a university, and you'll be supervised by a far greater number of people. But the principle is that you should be supervised by someone who is very, very competent in that particular field. Nice,
that's really cool. It's quite impressive how many specialists there are. I can imagine a lot of prospective students thinking that there might be one teacher who does all of the supervisions, but it's quite interesting to find out how there's so many. I was wondering which courses do you do supervisions for or lectures for?
Me, myself? Okay. So my research, my interests are really on the theoretical physics side of things. The course I'm lecturing this term is Advanced Quantum Field Theory, and that's a Part 3 course. So it's in the fourth year. It's in the fourth year integrated masters. But I supervise about half of the applied courses in the first year. So that would be classical mechanics, relativity, some linear algebra. In the second year, I'll do some differential equations. I'll do quantum mechanics, which I enjoy a lot, electricity and magnetism. And then occasionally I might do some quantum mechanics or general relativity supervisions for the third year.
Nice.
And to a large extent, the supervisors do sort of get to choose what courses they're supervising. So another benefit is that you're supervised by people who, at least in principle, are quite enthusiastic about the subject they're studying.
Yeah, and I guess, I think it's one of those things that students don't think about, but it does make a huge difference in if a university has a structure where the academics actively choose what they want to teach compared to if they don't. And then, as you say,
I think it gets really interesting as well when you're being taught by someone who's actually doing some active research in that area, because they can not only help you with the problems in the course as well, they can give you a wider context. They can explain why this is in the course, why this isn't in the course, for example, and how this fits in. And also, I think what a number of students don't realise is the divisions of areas of mathematics into different subjects is to a certain extent a little bit arbitrary. It's done for kind of bureaucratic organisational reasons, but there are lots of overlaps, and you see ideas, say in linear algebra, propping up in quantum mechanics or solving differential equations. And so it's very useful to be taught by someone who has enough perspective and experience that they can actually point out these interesting features that you might otherwise miss.
Are there do you have any examples of how the undergraduate maths course relates to the research that you're doing or have done?
Yeah, I guess so. So a course that I taught last term is quantum mechanics. It's a course I enjoy teaching because it's a fun course. And one of the things I'll be teaching this term will be classical mechanics, which will include classical gravity, orbital mechanics, things like that, and a bit of relativity. And one of the things I'm most interested in my research is how we build a quantum theory of gravity. So there's the quantum mechanics on one side, which is a general descriptive set of principles we think laws of nature should adhere to. And on the other side, there's gravity, the best description of which we have is general relativity, which you can learn in the third year. And you do find when you're teaching students, you find yourself kind of reassessing some of the assumptions and the axioms that go into something. So it's a really helpful thing to do. And it sets your kind of, exactly. And it sets your mind on, and often you get some great questions from students who aren't indoctrinated into the way of thinking about a subject, and they say, "But hey, what about this?" And it really tests your knowledge, but it perhaps gets you thinking, because you sense that you should be able to answer the question, and you want to say, "Well, things aren't that simple," but actually, why not? Why can't you give an answer to it? So
nice.
Yeah, it can be very rewarding.
That's really cool. It sounds really exciting as well. I mean, the inquiry of the where quantum mechanics has a place in gravity sounds really exciting. And I think I can imagine a lot of students, prospective students, trying to work out which courses to apply to. I can see them wanting to study maths in order to go explore that topic. Going back to supervisions, are supervisions in maths like school classes where you turn up and you're taught something for an hour, or do you have to hand in work beforehand and go over work out? What does it look like for the maths students?
Yeah, that's a good question, because I've mentioned this word supervision, but I haven't actually said what that is. So it's very different from a class. It's definitely not meant to be passive. So the way it would work is a lecturer who's lecturing a course will prepare some questions on a problem sheet. And before the supervision, a student would do their best to solve those problems and hand their work in to their supervisor. And as a starting point, the supervisor will go through some of those problems with the student, particularly if there are some misunderstandings, there are bits they couldn't do. But in some sense, those problems are meant as a sort of a springboard for a more general conversation about the topic, partly to try and kind of weed out any misconceptions or misunderstandings a student may have, clarify any points that they're still puzzled with, but also to try and develop their interest, to kind of see how, as I said before, these ideas fit in with other things. So I think the most effective supervisions are where the students perhaps talk to each other about the problems and come into the supervision with a plan saying, yeah, we don't understand how you solve Maxwell's equations in this case. Let's get him to tell us, teach us. And it won't be like that. It won't be a lecture on this thing, but it'll be a dialogue. And that's useful because supervisions are a tremendous resource. You've got someone who, in principle, should be able to answer any questions you've got. In practice, we're not omnipotent, but we'll certainly kind of help work through a problem together. And that's often where it's most fun, when a student asks a question, supervisor doesn't quite know the answer, but has a pretty good idea how to get to the answer, and you can work it through together, like a kind of almost like a mini research problem.
Yeah, nice.
I think but it does take a while for students to learn how to best use supervisions. So very often first years are a bit worried. They kind of feel that they need to impress their supervisors. They don't. The relationship's going to be a long one, right? Particularly with your director of studies, right? They'll know you for 3, maybe 4 years. So they will get to you. You won't be able to hide anything from them. But it's not really about impressing your supervisor. It's about kind of using them as a resource to kind of suck them dry of knowledge and understanding of the subject.
Yeah, I guess in a perfect world, most of the work happens before the supervision, and you have a list of specific questions you want to ask the supervisor.
That's right. And then there'll be, as you say, most of the work would happen beforehand, and then there should be a little bit of work that happens afterwards, right? Because there'll be some things that are clarified in supervision, and you shouldn't just kind of bank them and move on to the next thing. You should kind of take a moment to think about those things before moving on.
Yeah, that's one thing I wish I did more as a student, because it's easy after a supervision or tutorial to think that that's done, but you do actually gain a lot of more understanding by making sure you go over it one more time.
And it's particularly tricky in an environment such as Cambridge, where the terms are very short, things move quite quickly. Yeah. So once one supervision is done, you're probably staring in the face the deadline for the next supervision, and the pressure is to kind of try and manage the time well so that you can still make use of what you've just learned in the previous supervision.
Yeah, and it's fresh in your brain, so it's a good opportunity to make sure you consolidate that before you move on, I guess.
Yeah.
Nice. So just for the viewers who to explain what's expected of them in the first year, so am I right in thinking in a typical week, 12 hours of lectures, 2 problem sheets for 2 supervisions, which are typically an hour long.
Yeah.
Nice.
Yeah, that's about right.
Nice. That's really cool. So the next thing that we have here is with regards to course structure. So I believe you said the first year was compulsory, and how much module choice is there after the first year?
Okay. So there's a slight caveat, which I think we'll get onto later.
Yeah.
About the first year the courses being compulsory. They are compulsory. They're slightly different if you're doing mathematics or physics. We'll talk about that later. So, but in general, they are compulsory. Yeah. And I think that's true of any maths degree anywhere across the world. The idea being that there's certain ideas you need to have under your belt, you need to have understood before you can move on to the next step. It's like a pyramid structure in maths, very much so. And so it's kind of all the foundational core stuff is in the first year, and it's sort of non-negotiable. And I think you'd find that in every institution.
Actually, before going on to the second year, then, like for anyone who's watching and they're like keen readers and they want to read ahead with regards to maths, what would you say are like the key cornerstones that make up that pyramid in the first year that are building blocks for later on in the maths course?
Okay, so the key competences are some applied maths, so understanding how to solve basic differential equations, some linear algebra, a bit of classical mechanics, some probability. We'll come on to statistics later, but really kind of foundational bits of probability, some analysis, and that covers most things. Also a bit of group theory as well. And in terms of people sort of looking ahead to perhaps applying to university to do maths, there are a number of really good books out there now that aim to bridge the gap between specifically A levels, what you learn there, and university mathematics. So if you've come through the UK system, you will have seen quite a lot of applied maths. You will have done quite a lot of calculus. A levels are very much problem solving oriented, whereas if you come from a different country, you may have seen a bit more pure maths. So one of the things you might want to do is have a look at what you haven't done. So if you've been through the UK system, then perhaps have a look at some analysis. There's a great book by, I think, Laura Alcock, who gives a sort of student's first guide to analysis. But there are lots of books titled things like how preparing for university mathematics, or how to think about mathematics. But I think the most important thing to do is try and find something that interests you and just follow it up, because you will learn this stuff during your degree. But if you can find something that excites you and interests you, that is different from what you've seen before, I think that's a good thing. It broadens your horizons a little.
It's interesting to, it's new for me to describe calculus as applied maths. What is it about calculus that makes it applied rather than pure?
So I should be careful, actually. So it sort of it almost diverges a little bit when you get to university. So you'll do calculus in sort of two very different ways. Okay. So you'll do some calculus as a way of solving differential equations and calculating things like in vector calculus. So vector calculus is sort of a mashup of calculus and geometry. And that's very much tends to be taught with an applied feel. It doesn't have to be, but it tends to be, because the emphasis and the motivation is problem solving, and you will use those as basic tools to describe things in, say, theoretical physics, fluid dynamics, for example. The other branch of calculus, or the other guise in which you'll see calculus at university, is an analysis, which really, instead of developing the tools that you have of calculus, it's really understanding what makes calculus tick. Kind of, why can we rigorously prove what we're doing? When can you not differentiate a function? What does an integral really mean? And are there different ways of defining what you mean by an integral? So in some sense, you meet calculus in two different guises: as an application to more and more complicated and interesting problems, but also to try and put it on a really rigorous footing. So yeah, so it's pretty ubiquitous, and you'll see pure and applied mathematicians using it.
Hopefully this isn't. Is it? I don't know if this is a crude definition, but so do things fall under pure maths when we're trying to define things, define what they are?
Yeah, what we think of as pure math does change in time, but to a certain extent, I think it's almost a self-identifying quality. So pure maths tends to move more slowly and tends to try and prove theorems as rigorously, so that you know something is true and you understand the limits of which a theorem or a statement is applicable. And that can often involve very novel ways of connecting different areas of mathematics. But the ultimate product is always a theorem, right? And this is whether a theorem is of interest or not is regardless of whether it's applicable to describing some phenomenon in nature. Whereas applied mathematics and theoretical physics, usually you're using the maths as a tool to do something. You're not studying it purely for its own sake. So you may want to understand gravity, for example, and in order to understand gravity, as Einstein described it, you need to learn quite a lot of geometry. So you need to learn how to deal with higher dimensional geometry. So there's a lot of kind of sophisticated mathematics, but you're learning it for a purpose, like it's to be applied to something. Now, like most distinctions, there comes a point where it's a little bit artificial and unhelpful, right? Because a lot of the mathematics that we consider as pure, in its history, it has its origins in problem solving, right? Today, a lot of at the sort of frontier of some of the mathematics some of the theoretical physics we're trying to understand, we're bumping into our limits of what we understand in mathematics. And so an area I'm particularly interested in, string theory, seems to be suggesting, and has suggested in many cases, mathematical structures that were unexpected and we don't fully understand. So there's often a chicken and egg quality to this. And often what happens is applied mathematics gives rise to a problem that is of interest to them. Pure mathematicians say this is more generally of interest, try and understand the mathematics to a deeper and more rigorous level. And then that is then applied again to the so it's not quite a clean distinction. To a certain extent, it's where your focus is, what you care about, why you're doing it.
Interesting.
It's a very long and rambling answer to a very simple question.
But yeah, but I think it's really a distinction that most people wouldn't have no idea, not even really know where to start. This is going to go a bit off topic, but would you be able to explain to us who don't know what string theory is, like a brief explanation of what is string theory?
Sure. It's a proposed answer to a question. So let me tell you what the question is. This is one of my favourite topics, so you should rein me in. Waffle on for too long. So at the beginning of near the beginning of the 20th century, so about 100 years ago, we had two major revolutions in our understanding of the real world. One was relativity. This was most notably general relativity, which is Einstein's theory of gravity, and it describes gravity in terms of properties that space and time can have. This is useful in the study of sort of black holes, Big Bang, cosmology, things on very large scales traditionally. The other big revolution we had, which in many ways was much more profound, was quantum theory. And unlike relativity, which is really a theory of gravity and space and time, quantum theory is more a set of principles that we think all physical theories should adhere, all laws of nature should adhere to. And so we have quantum theories of electricity, magnetism, the nuclear forces. It's no coincidence that the sort of big technological revolution we've had over the last 100 years started about the same time we discovered quantum theory. And there's a reason why we suddenly could do a lot more, because we understood a heck of a lot more. And so we've got quantum theories of pretty much everything we've ever seen, apart from the first thing we ever saw, which was gravity. The first force that was ever studied was gravity, and we've got Einstein's description of it in terms of space and time, but we don't have a quantum theory of gravity. And there's something about the principles of quantum theory that seem to not quite sit nicely with the principles that are underlying general relativity. So the big question that I alluded to is, can we find a quantum theory of gravity? Right. And we've been looking for a little over 100 years now, and we don't have a definitive set of principles and a mathematical structure we can point to and say, that's a theory of quantum gravity, or that's the theory of quantum gravity that describes our world. Progress has been very slow. And there are a number of reasons for that. One is, in the past, when we haven't understood how something works in nature, we go and have a look. We do experiments, like particle colliders, we bang things together. But quantum effects are noticeable generally on very small subatomic scales. Gravitational effects are notable when you have things the size of planets and suns. So there are very few experiments you can point to where you could study quantum gravitational effects. Black holes may give us an interesting playground to do that. But they're not so accessible. So what is string theory? Coming around to the question you actually asked. String theory is, it's a theory, so a mathematical construction, a set of ideas, given kind of very tight mathematical expression, that it's definitely a quantum theory, and it also contains gravity. So you can see general relativity coming out of it. So you say, well, why do I say we don't have a final quantum theory of gravity yet then? Well, two reasons. There's still an awful lot about string theory that we don't understand. So it's definitely not in its final form. We don't understand the principles that underlie it. which is why, in some sense, I'm explaining what it is in terms of the question it's trying to ask, other than any kind of concrete statement of what I think it is. Also, we don't know enough about quantum gravity to say whether there's a unique solution to the problem of what is the theory of quantum gravity. So it may be that string theory, when we've got it fully developed and we understand it as a quantum theory of gravity, it may not be the one that quite describes the world we live in. But it's the best lead I would say it's the best lead we have at the moment, because it clearly has the two main ingredients. And it's exciting because these two revolutions I talked about 100 years ago, it very much feels like they weren't isolated revolutions on their own. They were the beginnings of something much, much bigger that we're right in the middle of. And we don't know whether we're going to get to a quantum theory of gravity tomorrow. Maybe someone's going to publish a paper that will explain everything, or if it'll be 200 years' time. We don't know.
Interesting. So I still have a few questions. I guess I have two questions. I guess one is, why is it called string theory? And another, I guess, where does it come from, and what constitutes it at the moment, even if it's not fully formed? You see what I mean?
Sure. Okay, so they're all kind of related questions, I think. So the first one was kind of, why is it called string theory? So we don't understand what the principles of the theory are and how best to think about it. Our best way of thinking about it at the moment is in terms of making a very simple kind of, almost seems very mundane generalization of, instead of thinking of the fundamental building blocks of nature as being point-like particles, think of them as extended objects. So imagine a little loop, and that's the string that you would talk of. That's probably not quite the right way to think about it, in the same way that particles aren't really the right way of thinking about fundamental building blocks of nature, but they were kind of a gateway into a deeper understanding. And this kind of picture of strings is probably a gateway into something. It's definitely a gateway into something much, much deeper. Where it came from is sort of by accident. People weren't trying to understand quantum gravity. It's sort of in the late 60s, early 70s, people were trying to understand the strong nuclear force. So the force that binds quarks together to form protons and neutrons, kind of the basic building blocks of atomic nuclei. And that was a very new physics then. Particle accelerators weren't as sophisticated as they are now. We knew much less. And it wasn't clear that whether or not the physics of the strong force would be similar to what we'd seen already in electricity and magnetism, or required something radically different. One thing was known is, if you take two quarks, two subatomic particles, and you try and pull them together, a bit like a rubber band, the further you pull them, the harder it gets, the stronger the force pulling them together gets. So an early model that was hoping to capture some of this physics was as a little string, with the quarks being an endpoint, and then if you try to pull them too far apart, the string snaps and you get two endpoints. Two sets of endpoints. And people tried to use this to describe the strong nuclear force, and it captured some of the properties, but this annoying feature that kept on coming back is that whenever you calculated anything with it, you got gravitational answers out, right? So you try and look at some interaction between nuclei using these things, and it would give you some answer that involved gravity. And there was no way of removing gravity. And so people thought, well, this model doesn't work. And other people picked up the model and said, aha, this might be just what we're looking for. This is a quantum theory you've built, and it knows about gravity. In fact, it has to know about gravity. You can't get away from it knowing about gravity. In some sense, it sort of predicts the existence of gravity if you didn't know about it beforehand. So we stumbled upon it completely by accident. It's often described as a bit of 21st century physics or mathematics that fell into the 20th century accidentally. And one of the things that's been quite interesting about it is that it hasn't just had impact in theoretical physics, it's also had impact in pure mathematics as well. There have been links between areas of topology and geometry, say, that were not thought to be connected in the way they are. And string theory somehow shows you that these things are two ways of looking at the same sort of thing. So there's some very deep mathematics. It's not just we don't understand the physical principles, we clearly don't understand the mathematics underlying what makes this tick. So it feels a little bit like we're trying to do sort of Newtonian physics without the benefit of calculus.
I see.
So we just don't have the basic tools yet.
That is, that's really interesting. I think it's really clear if anyone is listening as well. Seeing where it comes from in terms of the nuclear force between the two nuclei and that snapping, and and I think there's something very genuine. There's something very genuine about that origin story, in that the physicists did not want gravity to be there, and I guess But if they found that presence, it kind of I guess it makes it more believable, because they actually didn't want that to be there, but that's what they found. If you see what I mean,
right? It's a slightly more pure origin, so it's not loaded with an agenda or a way of someone saying, "I think things should be like this." It sort of comes out of it's sort of naturally out of some structure.
Yeah, and I guess it shows how collaborative like the world of science can be, when you find answers to your problems in completely unexpected places.
Yeah, serendipity.
Yeah, nice. With regards to I'm trying to bring it back to the course structure. We were mentioning before how even from the very beginning, actually before we talk about the two different pathways, how much flexibility or module choice is there in the second and third year?
Okay, so as we said, the first year is kind of just pretty much compulsory. The second year, there's a bit more choice, and we don't have complete freedom. There are some core things that every director of studies will encourage every student to engage with. But there is some flexibility. So you can sort of shift your center of mass. Maybe if you found that you don't like the applied stuff so much, but you're really fascinated by probability and where that may lead, there's chances to do things like statistics, Markov processes if you want, or similarly, you can move more towards the pure side. And in that case, again, you might end up being supervised in a more intercollegiate way, depending on sort of where the expertise is amongst the colleges. And then when it comes to the third year, sort of all bets are off, right? There's a huge range of courses. And no one could possibly do all of them. They're just a vast number. So you can do anything from general relativity to number theory to Galois theory to machine learning to financial models. To mathematical biology. There's a huge range of subjects. And then the basic teaching method is the same. It's lectures and supervisions, but the supervisions take on a truly intercollegiate nature. We start to behave more like a university at that stage, and no one college has the expertise to supervise all the subjects. So there's lots of moving around and being supervised. And it gives you an opportunity potentially to be supervised with students from other colleges, which is a nice way of sort of branching out a bit.
Nice. And is that because I believe in the maths course, there's an opportunity to turn it into a master's, like do a fourth year?
There is. So we have this thing called Part 3 Maths. It's probably the oldest examined mathematics course in the world.
And Part 3 means fourth year?
Yes, it does. That's a good point. Yeah. So yeah, we have we have Part 1A, which is the first year, Part 1B, which is the second year, Part 2, which is the third year. And at the end of Part 2, the majority of students graduate and leave. But if you want to stay, and if you got a first or a very, very high 2-1, you can stay to do Part 3, the fourth year.
Yeah.
And that's and for students who came up through the Cambridge system for the first 3 years, that's an integrated master's. And they constitute probably about a third of the number of students taking Part 3, and the other 2/3, are students who have come in from outside who are taking Part 3 as a master's. But it makes no difference. Whether you did your undergraduate here or elsewhere, that you would do the same course, sit the same exams, go to the same lectures. And that truly is, there's a huge scope there. And a difference with Part 3 is that there are no supervisions. So the faculty arranges the teaching, all of the teaching, and that will include small classrooms, so small classes.
No, that sounds really exciting. As is more just as a, I guess, lifestyle and socially compared to the first 3 years. That fourth year, you imagine you get to meet so many more different, like so many more people who've come from all across the world, different universities, and different coming from different undergraduate courses. Sounds like quite different to the first 3 years.
That's right. I think it is, and it's because you have such a large number of people coming from outside. It does change the feel of the course. I think students tend to feel much more department and faculty based at that time, so they won't have any teaching in college. College will really be there for kind of housing, tutorials, pastoral support, and also just your sort of home. But you'll start to have friends in many other colleges, and it's nice. And it's almost like a transition back to the real world.
Of course, exactly. And to go back to the very start of the course, I believe that there's two different pathways that a student can start on when it with regards to beginning their maths course at Cambridge. Could you explain what those two are?
That's right. So you can formally apply for two courses. There's the standard maths course. I think it's called Pure and Applied Maths. That's the standard maths course. The other thing you can apply for, and it's not a full course, I'll have to explain a little bit about what it is maths with physics. So the first thing to say is the entry requirements and the method of assessment on entry is exactly the same for both. Maths with physics differs from maths only in the first year.
Okay.
And in that first year, if you choose to do maths with physics, 3/4 of what you do is exactly the same as if you were doing straight maths.
Yep.
Where it differs is that one course from each term won't be delivered by the maths faculty, it'll be delivered as part of the natural science tripos. So the idea is instead of you learning dynamics and relativity, in the maths faculty, you'll learn similar courses in the natural sciences tripos, so Cavendish Lab, and the emphasis will be probably more on kind of some of the ideas that will come up later on in the natural sciences physics tripos. You'll also get some exposure to practicals as well, which you wouldn't get in the maths course. By the end of the first year, if you're doing maths with physics, you need to make a decision, because maths with physics comes to an end at the end of the first year, and you need to decide either to continue as a mathematician or to become a natural scientist. Okay, and you can sort of make this decision almost at any point, right? So in some sense, it doesn't matter too much which you apply for. At Trinity Hall, other colleges may care, but we're quite flexible. If people want to sort of apply for one thing, then change when they get here, it doesn't really matter. But the entry requirements are exactly the same, and you'll be admitted on the basis of kind of interviews with the maths fellows and so on.
I imagine you can't start doing natural sciences and then move on to the maths course.
No, that's right. So maths with physics is very much something that's offered by the maths faculty, but it is possible. We do some of the things in conjunction with the natural sciences tripos, and it's possible to move over to the natural sciences tripos at the end of the year.
But always from maths, starting with maths.
Exactly, yeah.
Nice.
That's right.
That's really interesting. And is it, so if you're doing maths and physics for that first year, and one of your supervisions per one of your lecture courses per term is from the natural sciences course, is it a specific maths lecture course that's omitted?
That's right, yeah. So in the first term, it'll be numbers and sets, which is like an introduction to analysis, and that would be admitted in favour of something in the natural sciences tripos. And then in the second term, it would be dynamics and relativity, so it's like a classical mechanics course, would be admitted in favour of something very similar, but taught in a slightly more, in a way that's geared more towards what might come later in natural sciences. Now, what we try to do, and certainly what we recommend, is that students at the very least sit in on lectures for those courses they would miss, so that if they were to do maths with physics in the first year and then stay on as a mathematician, then they haven't really missed very much. But yeah, you wouldn't choose which course you. So that's a good reason for for those particular courses to be the ones that you swap out.
So it's important for them to think how important is the number and set lecture course to them, I guess.
I think so. We'd still, as most directors of studies would recommend, they still at least go to the lectures in numbers and sets. So so the catch up isn't so much. Yeah. But the terms are very short here, but the vacations are very long. And part of the deal is we expect you to do some work in the vacations. So if you did maths with physics, then you move to maths for your second and third years, then one of the things we do is make sure that by the time you start the second year, you've covered everything you need to.
Oh, nice. Yeah, that's great, because I mean, yeah, I can see then from that perspective, you do have two choices, and there are avenues where you won't be behind, which I think is really cool.
Yeah, and I think it reflects the fact that theoretical physics has an interesting history in Cambridge. It's kind of rooted in the maths department, but there's a lot of theoretical physics that happens there. And if you're applying to Cambridge and you're interested in theoretical physics, it's not immediately obvious where you benefit most, doing natural sciences, physics, or maths. So it gives you that opportunity to not commit to a decision until you really know a little bit more about what you'd be doing.
Yeah, that is really interesting. I can see where the motive comes from, and I think it says a lot about the university and the departments when you realise how well thought out the courses are, and the pathways that they provide students to be able to choose from. On a different topic, so we get this question a lot in the admissions department when it comes to studying maths at Cambridge, because I think you can find the specifics of this on the Cambridge website, but when you're applying to study an undergraduate course at Cambridge and English is your second language, there's a language requirement, and how you meet that language requirement is on the website. But with something like maths, where I mean, as an outsider, I can clearly see how a maths course isn't the same as studying English at Cambridge. So, how important is a proficiency in English needed in order to do well in the maths course?
Okay, I think perhaps it's counterintuitive, but I think it is very important still. So a thing to remember is that all of the teaching, all the lectures, all the discussions that we have in supervisions, all the explanations, all of that will be done in English. So the maths is challenging. It's exciting, it's interesting, but it is challenging, and it moves at quite a fast pace. And you don't want there to be a language as an additional barrier to you developing into the best mathematician you can possibly be. So we do think that is important. And the other thing is something that is often a surprise to first year students is that maths can actually be quite wordy, right? If you open a textbook, a lot of the best textbooks are actually, there's quite a lot of verbiage in there. There's a lot written down, and lectures can often be quite wordy. And actually that shouldn't come as too much of a surprise, because when people say, well, what constitutes a proof? What do you mean by a proof? And a proof is nothing more than an explanation of why something is true. And good explanations, it's rare that they don't have any words in them. But also trying to, if you can imagine a situation in which someone is struggling with a particular area, and in a supervision, they've thought about it beforehand, they say, I don't understand this, can we talk about this? And we go, sure. There's going to be a discussion there. It's not just going to be people writing maths in silence. That's probably a good explanation. Good teaching is going to have a lot of verbal communication as well. So it is important.
Yeah, I guess, yeah. So there's in terms of excelling in the course, there's the maths, and then there's the learning, which is all done in English, and then there is a huge overlap in between, I guess, because I imagine when you're doing your work, it's never just purely maths and no words or annotations.
Yeah, that's right. That's right. I don't have anything here to show. That's a podcast. I can't, if I show you stuff, it doesn't matter. But that's right. Yeah.
Nice. Um, Moving into another topic when it comes to admissions for maths, Cambridge has this famous, well-known admissions test called STEP. Can you tell us more about STEP and when do students take the STEP exams?
Sure. So it's kind that you call it famous. Probably infamous is it's probably more to the point. Okay, so most of the people who apply will have similar levels of qualifications. And we can't, unfortunately, make offers to everyone who applies. So there needs to be some way of sort of testing people that extra mile, just stretching them a little bit more so we can make some sort of informed judgment. And STEP is the way in which we do that. So if you apply, you'd be called to, we try to interview most people who apply in maths. And if as a result of that interview, you're made an offer, that offer will be conditioned on achieving a certain grade in STEP. So what is STEP? STEP is a pair of exams, confusingly called Step 2 and Step 3. Step 1 was sort of phased out about 3 or 4 years ago, I think, so it no longer exists. And they are 2 3-hour exams that you take, I think, around the middle of June. I'm not sure what the dates are this year, but they'll be on the website. And you need to register, I think probably by March to take STEP the following year. And they're 3-hour written exams. They don't involve any calculators. It's all kind of pen and paper calculations, as almost all of the degree maths would be. And they tend to be pitched at a level of sort of AS level maths, further maths as well. And they're designed to sort of stretch you a little bit, and we consider them not only a good way of making the admissions process as fair as possible, but also a way of preparing students for the type of mathematics that you'd study in Cambridge. So in terms of what you should do to prepare for STEP, it's like most maths exams, practice. Do lots and lots and lots and lots and lots of practice papers. If you Google STEP maths papers, or if you go to the Cambridge Maths faculty website, there's a tab you can click on for prospective undergraduates, and there's a link to not only past STEP papers, but also lots of STEP support, worked videos and things like that that's available there. But I cannot encourage people enough that if you're seriously thinking of applying, take STEP very seriously. Perhaps if I can throw some numbers into it, we probably have about 50 or 60 people who apply each year for maths. We'll aim to take on about 6 students, give or take.
Is that 50 or 60 to Trinity Hall?
Yes, to Trinity Hall. Yeah, not to Cambridge. It'd be fine. We could take everyone if it was just, but no, just to Trinity Hall. And we can take about six students. We'd love to take everyone, but we just can't do it. Of that number, probably 10 to 15 we'd make offers to. And of those who we make offers to, 4 or 5 will get through STEP. So you can see that the odds of having an interview and then getting an offer are not that dissimilar from getting an offer and getting through STEP. So I think it's really, really important to take STEP seriously and to sort of engage with it as soon as possible.
So does that also mean if you find yourself in a position where you're very confident, you've done loads of STEP papers and you feel very confident in doing STEP papers, and maybe have someone who's looking at your work and verifying that you're on the right track, then you're in a very strong position when it comes to Cambridge admissions for maths. Do you see what I mean?
Yeah, I think so. So I think that's right. I mean, doing lots of practices in STEP and it's nice to get to a stage if you can where you're confident. They're tricky. I'm not sure how many people
can
feel confident. And if there is someone or if your school can provide some assistance, that's fantastic. But there is a lot of support out there on the web as well.
Okay.
So even if your school isn't in a position to provide any assistance, there is assistance that's there. And independently making use of those sort of resources is quite good preparation for doing a university degree anyway and becoming a bit more self-sufficient. There is a converse to what you said. I wouldn't want people to sort of listen to this, pick up a step paper straight away, look at it and go, oh my goodness, I can't do that. I'm not going to apply. It's a process, right? You're a long way from sort of doing A levels and therefore
That's
step
true.
now. So think of it as a long game and just start that process sort of early. But don't be put off, because I don't think there's anyone who just opens a step paper and go, yeah, this is easy, this is trivial.
Yeah, of course. Yeah, and that's I think a consistent phenomena when it comes to problem solving degrees and subjects. Where do you have any advice for someone who would open a step paper, read the question, and just think, I have no idea where to start? In what kind of things can that student then do in order to try to solve that problem in front of them?
So there are a number of things they can do. I think the first thing is to just sort of just do a quick audit like a skills check of what you know how to solve at the moment. What is your course, whatever course you're doing, covered at the moment? Because it may be you just haven't covered this stuff yet. And okay, that's fine. Don't worry about it. But also sometimes the techniques that you need, the bit of maths knowledge you want to apply to a particular problem, isn't obvious at first sight. So maybe think laterally a bit, kind of just go through what sort of things you know, what might help with this. If you get really stumped, as I said, there's quite a lot of support on the web. There tends to be quite a lot, I think, of examiners' reports. So they give kind of a commentary on how students did with questions. That can give you some guidance. I think there may be 1 or 2 years as well where full solutions are given. I know there are some videos available where people have worked through step problems. So I think the first thing, if you open a page, look at a step question and just think, I've got no idea how to do this, join the club. I think that's going to be the first impressions of almost everyone. But if you find you're really, really stuck and there's no one you can ask, then have a look at the resources available. Have a think about which area of mathematics does this question fit into? What do I know about that area of mathematics? What tools, what are the sort of things I can do in that area of mathematics? And you might suddenly feel, okay, this is just a cleverly disguised version of a problem I've seen before. Or it may be that it's just not something you've touched yet. So you can always show it to a school teacher and they may say, oh yeah, we'll be covering that sort of thing next term. Don't worry about it.
And do you think when it comes to, like, because I imagine this is also something, like a situation that students might face when they're doing problem sheets, is like being persistent, like a skill that students would need, like is like helpful to learn when it comes to like doing maths?
Yeah, it's maths at any level, I think, even sort of research level, being persistent is really important, not giving up. I think also talking to other people. So it's quite common, because it's a competitive process, to get a place in universities like Cambridge. People often think that it is always a competitive process. And actually, once you get here, it's not. The intention is it's a collaborative process and you do talk to your peers and any other support that's available. But yeah, not giving up is important, and being persistent is important. And maybe it's okay to be stuck on something, take a break from it and come back to it. Just make sure you do come back. You don't have to do everything there and then.
Yeah, because I guess the more you do that, the more you realize and experience that it's actually fairly likely that the third or fourth go, you make a lot of progress with the problems that you're doing.
That's right. And the way research normally works, which is quite indicative and no one tells you before you start it, is that you normally try out most dead ends before you find the way through. But you come out of that process with a real understanding of not just what works, but why that works. And that's that's an important part of the learning process. So trying things and them not working is really, really important. It gives you a depth of learning that's not often appreciated.
I guess because I think a lot of people, when they open a step paper and they look at a question and they think, I don't know how to do this. I think I think what that person doesn't realize is that there is there is a version of themselves in the future that will look at that question and be able to do it. It's just, and there's
Exactly.
a journey in between.
Yeah, knowledge is a time-dependent process, right?
Yeah, exactly. And then I think students who want to study maths shouldn't get discouraged quickly, because I think everyone has that same feeling when they're looking at STEP.
Yeah, and that's one of the qualities we're really keen to see in our applicants, sort of a sense of persistence and not giving up. I mean, my field, quantum gravity, we've been banging our head against the wall for over 100 years now, but we're still going. We're making progress slowly.
Nice. And with STEP, do you need any prior existing knowledge in order to do the paper? As in, when I say prior existing knowledge, as in anything above the maths A level?
There'll often be some ideas from further maths that are in there. So if your school offers further maths, it's a good idea to take it. I mean, hopefully if you're thinking of doing maths at university, it's a no-brainer. You like maths and you want to do as much of it as possible. But if your school offers it, that helps a lot.
Nice.
Yeah. But that's another reason why it's a good idea to have a look at the STEP resources and the STEP papers well in advance beforehand, so you can kind of work out what you need to do.
So lastly, so in a given application year, students can only choose one of Oxford or Cambridge to apply to. So that means that students, when they're wanting to study maths and they're applying for universities, they have to choose between applying to Oxford or applying to Cambridge in a given year. I was wondering, do you what advice you had for students who are trying to choose between the two institutions and the two courses, and if you knew, are there many differences between the two courses as well?
Okay. So there are some differences, but they're relatively minor. I think both places try and teach maths to the same depth and breadth as each other. The precise courses each year on year will change a little bit, but the basic idea, like compulsory first year courses that cover the broad stretch, are very similar. There are some differences. So in Cambridge, there are the method of teaching is lectures and supervisions for all 3 years, and then the 4th year moves to lectures and classes. In Oxford, lectures and supervisions, they call them tutorials, is in the first 2 years, and then my understanding is it's more class-based with lectures in the 3rd and the 4th year. So there is that slight difference. Admissions is the general idea is the same, but they don't use STEP. They have a different test they use, but it serves the same purpose, and what you have to do well in it is the same sort of thing.
I think they take theirs in November, I think, rather than June.
Yeah, so I guess there's a little bit more time. But I think the differences between the two are probably not so important. I think on a kind of very gross level, the similarities are much more important. But the cities are quite different. So if people are thinking of wondering which one they want to apply to, then go to open days, go and visit these places. There's also the micro question of which college do you apply to, and that's the same sort of issue, right? Broadly speaking, it's a similar experience, but I don't know, it may come down to personal tastes, what you prefer.
No, yeah, I mean that's normally the advice I have when the courses are quite similar between the two institutions. I'd always recommend or compare the admissions process if there's any differences. Which one do you prefer? The course itself, but normally those two things are pretty similar. So then the city tends to be the biggest difference. Which one, and I think if a student said, "Oh, well, both universities were quite similar, both courses quite similar, but I really felt at home at this one," that's a very good reason.
Yeah, exactly. So I think there is, I suppose, one difference is the way in which statistics is treated. So statistics is a separate department in Oxford, and the statistics tends to have a more applied feel to it there. It's kind of a bit more theoretical, a bit more pure here. But I don't think it, generally what's required to do well in Oxford is the same as what's required to do well here. What we're looking for in applicants is kind of broadly the same thing, what they're looking for. And yeah, I did my undergraduate in Oxford. I don't have an axe to grind. I don't very much.
Nice.
I think this is fairly honest.
Mm.
Yeah, but I'd strongly recommend people go and visit. And while they're there, try and get around as many colleges as possible, because that also may matter to you.
Nice. And I guess for anyone who is interested, it's not you can't apply to both in a specific year, but you can always, if you were to be unsuccessful in the first year and you wanted to apply to the other, you can apply to both, but they just have to be in different years. Nice. Well, thanks so much, Ron. Such an interesting conversation about studying maths at Cambridge and the different avenues that it can take students. It was a real pleasure. And thanks for the viewers for watching, whether that's on YouTube or your podcasting platform. We've got more podcasts lined up with students talking about the courses at Cambridge, as well as the academics who teach them. So we'll see you soon.
Okay, thank you.
Nice. Oh.
My wife does the same thing, orders books by colour.
Oh, really? Nice.
And it looks really cool.
Nice. Yeah. I do. I like the middle one because it's like quite, it's quite nice. So these are all French books, and the publisher's Gallimard in the 1920s. A group of guys basically decided to make a publishing business, and all of the books were white, and they've really, like, most books now in France are like this kind of like white binding, which I think is pretty cool.
That is quite cool.
Yeah. And they were very generous with whatever they published, which I think is why people liked them. I think their kind of motto was, they would ask writers to not throw anything away, and they'll just find a way to publish it.
Right.
So you just get a lot of like random diaries between like certain days, which you'd think, I guess whoever wrote it would think will just like go to the bin.
Yeah.
But it's actually really cool.
And I guess they probably got hold of some quite interesting stuff because these people became quite famous later on. Yeah.
I think because they loved reading and literature. They were very in touch with upcoming writers who weren't famous, and then they became famous. But then they had all of their diaries from when they were.
Yeah.
So they kind of had like a vision that these people are worth investing in.
Yeah. Interesting.
Which is also like quite similar with the podcast. You don't really know who you're interviewing, if you see what I mean.
Yeah.
The architecture podcast. She very like firmly said that the architecture scene is the culture is the architect has like an idea and wants to implement it in the way that they kind of envision it, and kind of a piece of art for themselves and the company that's funding them. But she wants to go into the sphere and make the industry people serving and the community serving.
Right. I see. Okay. Yeah.
And she was like so strong, like so strong-minded with this idea. I wouldn't be surprised if 10, 15 years, if she went and did that. And we have that interview online of when she had the idea, which I think was like really cool.
Yeah.
Yeah. Because
I don't delete anything.
Exactly. Put everything in the archive. I was never big in going to the union at uni because it kind of seemed counterintuitive, because you're surrounded by these like very talented, hard-working students, and you have really no idea what they're going to go on to do. So I found them much more interesting than queuing 2 hours to like see a talk by a stranger.
Yeah.